So in this video, we're going to be talking about composite functions and combining functions. So this sometimes gets a little bit of confusing for students. So I want you to be very, very careful about it and really kind of follow closely. So one of the things I want to talk about is just combining functions. And when we do that, we can actually take any functions and find any of the basic arithmetic properties of it. So essentially, when I just say something like f plus g of x, it means that I want to take the entire function and add an entire another function. So over here, I have the square root of x and x cubed. Well, if I just add those functions together, it's pretty simple. If I subtract the functions from each other, it's pretty simple, except for, of course, in the difference, you have to remember to distribute the negative when necessary. In this case, it isn't, but if I had two functions where the second function had more than one term, I would have to distribute that. And we've seen this before in finding the profit function is revenue minus cost, and we have to remember to distribute that negative through the cost function. You can take the product of two functions, or you can take the quotient of two functions. Now, all of these things are going to be important when you guys decide to take Math121, those of you who are going to be going on, because there are derivative rules for all of these types of functions. And you'll have to be able to recognize which one it is. So this is very, very important for as you go on in mathematics. So let's talk about operations with functions. So if f of x is x squared and g of x is x minus 9, find the following functions and give their domains. Okay, so if we have f of x, f plus g of x, that just means that we just want the entire functions added together. So this is just x squared plus x minus 9. Just add the functions together. Simple. If I want f minus g of x, so that means f of x minus g of x, and it does not mean times. Do not multiply f minus g times x again. This means this. This means this. Again, I can't say it enough times. Does not mean times. Do not multiply an extra x. So here, times, well, this is f of x times g of x, not f times g times x again. It's just f times g. So let's finish this f of x minus g of x. X squared minus, now I have to put this in parentheses because I have a minus. And I have to remember to, distribute the negative. I know I say that a lot, but you can see what that becomes. Then f times g, okay, now I'm going to take x squared times x minus 9. Now I can distribute this if I want to. X cubed minus 9x squared. And then f divided by g of x, that's just f of x over g of x. So this is just a matter of notation. We're just taking the entire, this just means take the whole functions and make them in terms of x. So it's a little bit of a confusing notation, but it really means nothing more than that. So we have x squared over x minus 9, where x cannot be equal to 9, because it would make a denominator 0, and that's no fun. So I want you to think about these for a while. And these are fairly simple. So let's move on to, of course, revenue, cost, and profit. The demand for a certain electronic component, okay, I got too lazy to decide what they were, is given by P of X equals F500 minus X. Okay, that is the demand. So producing and selling X components involves a monthly fixed cost of $499. So this is price. So the price is based on demand, a demand function. And a production cost of $2 for each component. So let's write the equations that model total revenue and total cost as functions of the components produced and sold in a month. So remember our revenue function is price times units sold. So in this case, our price is P of X and our units sold is X. So now we are multiplying by X, but that's the number of units sold is X. So in a sense, if I said the number of units sold, I have another function that's f of x equals x. So I really want p times f of x, which is p of x times f of x, which is 500 minus x times x. And that's the simplest way, is basically I'm just taking this price and I'm multiplying by x. And that becomes 500x minus x squared. That's it. So that's my revenue. Now my cost function, remember, our cost function is unit cost times units plus fixed costs. Units is x, unit cost is 2, fixed cost is $4.99. So this is equal to 2x plus $4.99. So let's look at the next part of this example. Write the equation that models the profit. So remember, profit function, again, revenue minus cost. So our revenue function, looking back up here, is 500x minus x squared minus our cost function, which in parentheses, and you can even keep this in parentheses if it's easier for you. So let's figure this out. Oops, sorry. So this is 500x minus x squared minus 2x minus 499. So it looks like I have negative x squared minus 2x. Oops. 500 minus 2, which is 498x minus 499. This is plus, sorry. It's because I have 500x minus 2x. So this is what I have. This is my profit function. Capital P of x. I know, we like to do weird things in math. Sometimes we have capital P's and little p's. And so let's find the maximum possible monthly profit. So remember from chapter 3 that if we have a SAD graph, we have a maximum. So we know we have a maximum at the vertex. So let's find our x-coordinate of our vertex. That is negative b over 2a, which is negative 498 divided by 2 times, looks like a negative 1, which equals 498 divided by 2, which is 249. So now, in order to find the maximum possible monthly profit, we need to plug this in. And again, we can do this in a couple of different ways. You can use your calculator, or we can just multiply it, right? That's minus 499. Okay. Okay, so remember, this is negative positive 249 squared. So the negative is outside the square. So we're going to square first and then make it negative. So we're going to go negative 249. Oops, that was yesterday's. Negative 249. Whoops, I hit that button all the time. Squared plus 249 times 498 minus, and believe me, your calculator knows order of operations, so you don't have to worry about it. So I get 61,004. So that is our maximum monthly profit for this item. So let's talk a little bit about average cost. So the cost function is interesting. Most of the time, your cost function, you can't really minimize it many times, because a lot of times your cost function, especially something that just looks like this, if you have something that's 2x plus 499 like the previous problem, you can't minimize this because it would minimize at x equals 0, because if you do make anything, it doesn't cost you anything. So that's why we don't talk about that a lot. We've done a few problems when this is when the cost function is a parabola, but even then, that's a difficult situation to talk about. So what we talk about a lot of times is average cost, and that is the average cost per product. So what happens is this is just your cost function divided by x. So looking at the previous example, and it is denoted by a C with a line over the top of it, is 2x plus 499 divided by x. So this is just like a composite function or a combined function over x. So 2x over x, so I can divide this up into two pieces. And this, of course, x is greater than 0, because it can't be less than 0, because we can't produce negative quantities, and it can't be equal to 0 because of the denominator. So this is equal to 2 plus 499 over x. Well, this is something that I could look at and I could find the minimum function of. And that's something you're going to do more in applied calculus. You'll do more average cost functions. So let's talk about this one. Sunny's greenhouse produces roses, and their total cost for production of X 100 roses is 25x plus 250. So let's form the average cost function. 25, so C bar is C of x over x, which is 25x plus 250 over x. So that's 25 plus 250 over x. So there's our cost function, our average cost function. And for what values, is C bar defined? Let's give a real-world explanation of this average. So a couple of things we want to say is we know that C bar is defined for x greater than 0. Remember, input values are x's. So C bar is defined for x greater than 0. It doesn't make any sense. So what is a real-world explanation of this average? What is this actually telling us? This is telling us, so let's say, for example, that they sold 50 items. So they sold 50 100 roses, I suppose. So let's say they sold 50 100 roses. Then their cost function, their average cost, is 25 plus 250 over 50, which is 25 plus 250 over 50 would be 5. So $30 per 100 roses. So on average, it costs them $30 to produce 100 roses. On average. That doesn't mean that each rose costs $30. That means on average, it costs them $30 when they're selling 50 100 roses. Now, 100. I know, it sounds weird. 55,000 is what it is. So, but of course this is going to change, because if they were to sell, let's say 100 roses, their average cost is actually going to drop, because think about it, their fixed cost is getting split among more roses. Because that's basically what's happening, because this is getting split among more roses, and therefore that cost, that average cost actually is going down as they make more. So the real world explanation for the average is, this is the average cost of producing X hundred roses. So that's basically what it is. It's the average cost, not the cost. So in other words, if they produce X hundred roses, it will cost, on average, about C bar dollars per 100. So that's essentially what they're trying to say. If they produce X hundred roses, it will cost, on average, about C dollars per 100 roses. So let's graph C bar for 0 to 2,500 roses. So let's remember our C bar was 25 plus 250 over X. So let's take a look. Let's see what that looks like. So let's go into our Y equals. Let's clear these out. And let's go 25 plus 250 divided by X. Now it's telling us in the window that we want to go from 0 to 2,500. Here, we'll make this. And we'll make it 50. That'll look good. And then our Y min, well, I know I'm not going to have less than 0 average cost. And I don't think my average cost is going to quite go up to 5,000, even if I do 2,500 roses. So I'm thinking that 100 will be more than enough to show me what I want to see. Make that 10. Let's graph that now. And that's what it does. You didn't even need to go up to 100. But you can see what happens in this case. You can see that it kind of levels off after a while. And in fact, let's go back up here. What would 1 be? That would be, see, we don't even need to go that high. Let's go 1. I guess 1 would be 2. Yeah, that's fine. We'll leave it where it is. So let's just take a look at this real quick. And let's think about what's going on here. So it looks like we have a situation like this. So this pretty much levels off. Oh, 2,500 roses. Oh, I made a mistake. This is 25 units. Okay, let's go back and fix that. That should say 25. Yeah, that'll be different. But it was interesting to see what happened in that case. See, I wasn't careful. Okay. So now it looks like this. So now we can say that the average cost drops as x increases, and will eventually level off. So this is eventually going to level off, which we actually did see when we did 2 million roses, I suppose. Or, well, 250,000 roses. So, now let's talk about, so this is what we have to do when we're talking about our combining functions. So let's talk a little bit about composite functions. So you have seen this before. We have our fogs and our goths, and I know you've seen it. This simply means we have f of g of x. Okay, so now we're taking the function of something else. And you've kind of seen this before when you plugged in x plus h in for x in the difference quotient. That's essentially what you're going to be doing. You have a new function that you're plugging inside of another function. And you can also go the other way. And they're not always the same thing. So let's take a look at composite functions. So this is my joke here. So if anybody has seen Inception, I call this functionception. So functionception, that's what we're doing right now. So do you know what a composite function is? So he's talking to him. No, it's a function within a function. So there you go. Functionception. So if you think about a function like a machine, which I like to, I like my toaster analogy, then, or my making pizza, I have another analogy about making pizza. So a function, a composite function is a function of a function. So in other words, we input, in this case, to make pizza, we input all the ingredients for the pizza. Then we create the function g is putting the pizza together. And then we take basically a Papa Murphy's pizza and we stick it in the oven and we get an output. Right? We get our pizza out here. So this is our ingredients. And then we take our, I think that's an E. Right? No, it's an A. So our first function is the person back there that takes the pizza, or the machine at Costco. They have a machine at Costco that actually makes pizza. And that's a function, right? Because it puts everything on there and it does everything. Then it goes to the oven. So here's the oven. And it gets cooked. Now, that's the outside function and the inside function, right? Well, the other way around. This is actually the function we have to do first. So this is the inside function. This first one is the one we do first. And then we have to put it in the oven. That's the outside function. We can't do it the other way. Does it work the other way? Not in this case, because if you do f of g, you get a pizza. What happens if you do g of f? What happens if you take all the ingredients and cook them in the oven and then put a pizza together? Just think about that for a second. It's going to be very different. It's not going to be the same if you do that. So it is very, very important that you follow the instructions. The inside gets done first. And so that's really, really important, because that's like what happened with putting in x plus h. You have to apply that function to x plus h first, then you can do other things. You couldn't just put the x in and then add h, because that's like putting all your ingredients for your pizza in your oven before you put them together. And that doesn't work. Not very well, anyway. I'm trying to imagine it in my head. I'm trying to put melted cheese that's coming out of the oven on top of a pizza, which I can't. On top of a basic piece of bread, piece of flatbread, and it doesn't work very well in my head. So let's talk about an example. So let's look at this, and let's say I want f, and this looks like this, fog of x. Again, not times. This is f of g of x. So what we want to do is g of x is x minus 2. So let's put the square root of x minus 2 in here. So this is f of the square root of x minus 2. So we want our function evaluated at that. So everywhere we see x, we plug in the square root of x minus 2 instead. So the square root of x minus 2, square that, and add 3. Well, the square root of x minus 2 and then squared is x minus 2 plus 3 is x plus 1. But if I go the other direction, that's not going to work. Okay, again, not times. This is outside function is g, and the inside function is f. So I have to do f first. So I put this function f goes in here. So this is g of x plus 3. So now this f, or this g, is going to take this, subtract 2, and then take the square root. So that is going to be the square root of x squared plus 3, I just put that in parentheses where x is, minus 2. So it takes my input, subtracts 2, and then takes the square root. So that is the square root of x plus x squared plus 3 minus 2, which is the square root of x squared plus 1. I cannot do any more. Because remember, a square root sign, you cannot take out one square if it's added to something else. If it's multiplied, you can. If it's added, you cannot. If there are terms added or subtracted under a square root, you can't get rid of it. Okay, so big difference in these problems. This, I squared the whole square root. Here, I had the square root of terms, so I can't do anything to it. This is an important concept that I want you guys to understand. It kind of shows up on tests a lot. Finding compositive finding compositive function outputs. Okay, so let's do this again. And I do a lot of examples of this simply because people do sometimes have issues with this, but it is really super important for you to understand this concept, especially if you're going to be moving on to the next class. And even if you are not, composite functions show up just about everywhere in mathematics. All right, so let's see what we've got here. We want h of f of x, and we're going to also talk about the domain of the new function. So we want h of, so first we put f of x. So f of x is 3x plus 1. So what we have is h evaluated at 3x minus 1, And then, but 3x minus 1, h of x takes x and takes the inverse, 1 over x. So we just want 1 over this, 1 over 3x minus 1. And if we look at the domain of this new function, we can see something here. x cannot be equal to 0, so 3x minus, or not, excuse me, the denominator can't be 0, so 3x minus 1 equals 0, so 3x equals 1, x equals 1/3. Or actually, it doesn't. So the domain is all real numbers except for 1/3. Now, f of g of x, we have f of what? G of x. So let's replace g of x with this, 4 minus x squared. So what does f do? F takes whatever's inside here, multiplies by 3, and then subtracts 1. So we're going to take, now instead of just x, it's 4 minus x squared. Multiply it by 3, subtract 1. And that equals 12, I'm just distributing this 3, minus 3x squared minus 1, or negative 3x squared plus 11. Now, is there any domain restrictions on this one? No. The domain is all real numbers. Negative infinity to infinity. Anything's allowed to be in there. So now we have g of f of x. So this is just the backwards of this one. So this is g of my 3x minus 1. So now g of x takes x, it squares it, and subtracts it from 4. So now I want to take this number right here. I want to square it and get it subtracted from 4. So that's going to be 4 minus, and now I've got to take this out, 9x squared minus 2 times 3x times 1, which is 6x plus 1. 4 minus 9x squared, distribute, plus 6x minus 1 equals negative 9x squared plus 6x plus 3. And we're done with that one. And again, the domain, since there's no domain restrictions, this one is also anything it wants to be. Okay. So let's talk a little bit about technology. Now, you can do all of this on your calculator. Now, you can't get it, you cannot do it algebraically. You can't get the algebraic function but you can graph them. You can find specific numbers. You can do a lot of different things. So let's take a look at how we would do this. So going back to one of my first examples, f of x equals x minus 2 and g of x equals x squared plus 3. So let's put these in for y1 and y2. The square root of x minus 2. We'll just delete the rest of this. Whoops, doesn't want to. X minus 2, and in y2, I'm going to put x squared plus 3. Okay, so this is going to be y1 is the square root of x minus 2. y2 is going to be x squared plus 3. And then what I'm going to do is I'm going to look at, I'm going to graph this on the window negative 112 by 0, 200. So I'm going to go to my window. Negative 112, 0 to 200. Oops, my scale's messed up. There. And that'll be fine. Okay, so let's graph that and see what it looks like. Oops, I forgot to graph x plus. So I forgot one thing. I need to graph x plus g. I just graphed these two functions. Sorry about that. So let's go down here, and I'm going to show you what you can do with this. So I actually want to graph y3. So now I'm going to go to y3, and I'm going to set y3 equal to y1 plus y2. And remember, to bring those up, I go vars over to y-vars. So vars, y-vars, function number 1 plus then I go vars, y-vars 2. So I'm going to go vars, y-vars, oops, enter, vars, y-vars, I forgot that one step, enter 2, enter 2. So now look, I've got y1 plus y2. So now what I'm going to do is I'm going to go over here and I'm going to turn off my graphs for y1 and y2 by clicking the equal sign. So I'm going to go up here, click the equal sign, and it comes off. Click the equal sign. Now you notice the only equal sign that's highlighted is y3. So let's graph it. And there it is. So let's think for a second. What does the domain of this appear to be? It looks to me like we can't start until this point right here. And that is at x equals 2. Which makes sense. Because remember, our function is the square root of x minus 2 plus x squared plus 3. So if we go less than 2, that's going to make this square root negative, and it's not going to be able to be graphed in the real numbers. So it looks like our domain is either we can say x is greater than or equal to 2, or we can say 2 to infinity. So we can actually see what the domain is. Okay, now let's talk a little bit about f over g of x. And remember, I'm going to say it again, not times. Okay, so now let's go back to y equals. Now instead of x1 plus x2, we have, or y1 plus y2, that's what I mean, we have divided by. And that's all we have to do. Just change it to divided by. Now, what's my window? Look, I made my window really small on the y's. So I went 0 to 40 and 0 to 0.1, because we have to do that sometimes, right? Let's make these, okay. Actually, let's make it 4. Okay. Let's graph this. Weird. Look at that weird thing. Okay. So this is kind of strange. What is the domain of this thing? Let's think about what it is. So this is f of g, f of x, over g of x, which is the square root of x minus 2 over x squared plus 3. So one question that I have for you, can this denominator ever be 0? No, because x squared cannot be equal to negative 3 in the real numbers. So again, the only issue is the positive 2. So again, that's the only problem, is that x has to be greater than or equal to 2, or again, 2 to infinity. So same domain on both of these. And another thing that this allows me to do is I can also look at f of g and g of f. In fact, I can graph them. And the way I would graph them would be like this. So instead of that, I would just go y1 parenthesis y2. Watch this. Oh, I need to stretch my window out a little bit, sorry. All right. Okay, so let's stretch our window out to, actually, you know what? Let's just zoom to standard and see what it looks like. That's what it looks like. That's f of g of x. And I could find out what that is at -1 because I could just go like this. I can go calc value -1. And at -1 looks to me like it's 1.414, which I actually recognize as the square root of 2. And you can actually do this directly on your calculator. You can bring up vars, y1 of, do this again, vars, y function 2 of -1, and get your answer that way. I can look at g of f also, g, because I can put, okay, let's clear this. Let's go vars, y function number 2. Then I can graph it this one too, which will be very, very different. So look at that. That is way different than the other one. And what we could do is we could actually find what that is at 5. So again, calc value 5, and this is 6. So those are some ways that you can actually use technology to do all of these interesting things with it. So we'll be doing some more in class. I have an activity that we will be doing with combinations of functions. That should be pretty fun. And that's like combinations of combinations of combinations of combinations. It's kind of crazy. So I will see everybody in class.